Hello, I'm Abby. We're 30K Structures. Welcome to our CDR presentation. This year, Structures only has two sub-teams. We're doing the payload couplings and the motor retainer. Our target factor of safety is 1.8 with a knockdown factor of 1.2 and an environmental knockdown factor of 1.1.
So first we're going to talk about the motor retainer. My name is Ronan.
I'm Adnan.
I'm Ryan.
I'm Devin.
I'm Brendan.
Okay, so the first design we explored was the aeropack retainer. This is comprised of two parts, the cap and the body, which are both labeled in the picture on the left. The aeropack itself is a COTS part that has been used in the past fairly reliably. The body of the aeropack is fixed to the thrust coupling via axial bolts. The thrust coupling is attached to the rocket via spring pins and epoxy, and the tail cone is fastened to the thrust coupling via radial bolts.
So for the load cases on the aeropack retainer, we have net section failure, lip shear, lip bending, pin shear, pin bending, bearing failure, and tear out. The loads applied during the thrust phase of the launch go through the blue section up until the thrust coupling, and then the loads for the recovery load go down on the cap of the aeropack retainer. All right, and then our main concerns for where we might see failure are the spring pins, so either shear or epoxy joint failure, thrust coupling shear, bearing failure, or tear out.
Okay, so exploring some of our hand calculations, all failure modes meet our target margin of 1, and most far surpass that. Some of the lower margins are boxed in red. The majority of these margins have easy fixes. So for lip bending on the thrust coupling, we have room to implement a larger lip to counteract that. And then for pin bending and shear on the spring pins, we can add more spring pins or use thicker spring pins.
So we did a von Mises analysis for the thrust coupling, and then with a resolution of about 18,000 elements, with the bottom part fixed, and then the thrust force applied to the top surface, which is represented by the purple arrows going down. So the stress analysis is represented on the heat map, and we found a minimum FOS of 9.
All right, so for manufacturing that thrust coupling, it should all be done in pretty much just one operation. We don't need any fixture plates, so that makes it pretty easy to do. We would be using the ST30 SSY, and some examples you can see up there, non-inclusive list, but we'd be doing turning, facing, drilling, boring, parting. And that's been done in the past. There's tried and true methods for manufacturing these, so we're not very worried about actually manufacturing them. When it comes to CAM, we want to have that done very soon. We hope to have it done within the first 2 weeks of C-term. That way we can start machining these as soon as possible.
All right, so moving on to our alternative motor retainer design, we have what we call the wedding cake plate retainer. The reason we're looking at alternative motor retainer designs is mainly because we want to see if we can find a lighter and more cost-effective motor retainer, and also see if we can have it better integrate with the tail cone. So at the top, it starts with the thrust coupling, which is spring pinned and epoxied to the body tube, which is then bolted to the first standoff, and the motor casing sits in between the first standoff and the second standoff, so the forward and aft plate.
For the load cases on the wedding cake retainer, they are pretty similar to the aeropack, but there's also some additional considerations because of the more complex geometry of this retainer. We are looking at the thrust coupling lip. We're looking at the spring pins and the epoxy tear out from or epoxy shear from the base of the thrust coupling in the airframe, and then tear out and bearing on both of the plates, as well as bolt shear. The epoxy joint is still kind of a rough idea right now. We need to determine whether or not the joint is sufficiently strong if we're using similar epoxy to last year, or if we're going to try a different approach to that. But we do have ways to increase the surface area of the epoxy just by making that shoulder a little bit longer if needed. We can determine that down the road. The thrust load is transmitted up through the forward plate, the blue plate there, up through the first set of standoffs into the lip of the thrust coupling, which goes right into the body tube. And then the recovery load is transmitted down through the aft plate, the red aft plate on the bottom there, and put stress on the fastening nuts on the bottom. For the hand calculations, again, there's a lot more considerations for this because there are multiple plates and fasteners, a lot more complex geometry than the Aeropack. Most margins are still well above 1.0, but there are a couple that are slightly lower. But our margin indicates that we're meeting our desired factor of safety as well as the additional knockdown factors. The ones that are quite low are labeled in the red boxes, and there are pretty simple solutions for most of them. The plate bearing stresses can be improved just by using a larger contact point for the fasteners, and that can just be adding washers to places that don't currently have washers or using larger washers to distribute that force better. The lip bending, the pin bending can be improved by just, again, more pins or larger pins, but right now it's meeting those standards. There's no real reason to need to improve that, but if we would like wider margins, we can do that. As well as the fastener margins on the far right side, we can just use slightly longer bolts because we do have room within those standoffs to use slightly longer bolts.
On this slide, we have the von Mises analysis for the motor retainer coupling for the wedding cake design. The thrust force is applied through the forwardmost standoffs that are highlighted in the purple region, and the green arrows show where the thrust coupling wall is fixed inside the airframe. It contains a total of 26,000 elements. However, we're hoping for future analysis, we can go higher, around 80,000 elements. The stress analysis is shown on the heat map, with the highest value being about 8.7 times 10 to the third PSI, with a thrust force of about 1,200 pounds. A thrust force of about 1,200 pounds is applied. Our yield strength is about 3.9 times 10 to the fourth, so that means we have a minimum factor of safety of 4.6. For this, this is the von Mises analysis for the aft plate and the forward plate of the wedding cake design. Similarly to the last design, the purple arrows indicate where the force is applied, and the small green arrows indicate where the model is fixed. The stress analysis is shown on the heat map, which is modeled for a force of, again, 1,200 pounds that's applied to the forward plate, which experiences the thrust force, and 197 pounds of force, which is applied to the aft plate, which experiences the recovery force. The aft plate has a minimum factor of safety of 3.8, while the forward plate is experiencing the most force and has a minimum factor of safety of 2.1.
For manufacturing the plates, so we'd be using some sort of CNC lathe. We could probably get away with using the 4-axis lathe. The biggest operation for those plates would be facing and parting, and it's not that hard to complete. Again, we want to have the cam done very, very soon. We hope to have that done within the first 2 weeks of C term. And for the couplings, like before, we'd be using ST30 SSY. It'd be all one operation, no fixture plate needed. It would be very, very similar to couplings done in the past. Again, we'd be doing cam in the first 2 weeks of C term, and that way we can manufacture them as soon as possible.
Right. So we've created a design matrix comparing the Aeropack retainer to the wedding cake plate retainer. In terms of machinability, the Aeropack will likely be bought, so we'll really only have to machine the thrust coupling, so more machining will be necessary for the plate retainer. In terms of cost, we have an Aeropack right now. If we reuse it, it will be cheaper than machining plates, but if we were to buy a new one, then the cost of the Aeropack will exceed the cost of machining the plates for the plate retainer. In terms of factor of safety, the simulations and hand calcs both yielded higher factor of safety for Aeropack compared to plate, but both still came out good. terms of tail cone integration, we're still working on a design for the aeropack where the radial bolts and axial bolts don't intersect. In terms of weight, the plate assembly itself is lighter than the aeropack, so it's rated higher on that. And the aeropack has a much simpler assembly. There's just more parts to go with the wedding cake plate design. So, yeah.
All right, now we'll go over the design of our payload couplings. I'm Jaden. So here's the designs of our payload couplings. On the left, we have the nose cone coupling, and on the right, we have our recovery coupling. The nose cone coupling uses spring pins and epoxy, while the recovery coupling uses radial bolts and epoxy. On top of that, the recovery coupling has a gasket to help prevent the pressure changes. For loads, we're mostly looking at epoxy shear, bolt shear, and then simple and complex tear out in both of the coupling and the coupling tube. And we're focused on the recovery loads, which act on opposite directions for the recovery and nose cone couplings.
We ran von Mises analysis using the expected recovery load of 1,197 pound force. However, this von Mises analysis was run with the loads placed in the wrong direction and wrong place. We will be done with the resimulation by the first week of C term. Regardless of the inaccurate simulation, the way we ran the factor of safety, which was a minimum of 11, so we expect that when we rerun it, the factor of safety is still within the target. For the calculations, along with the simulation, we can the parts margin and the coupler tube margins all have no single failure mode, and so they're not close to the critical, so everything's comfortably within the required factors of safety.
In terms of manufacturing the payload couplings, it's pretty straightforward. We've done in the past. There definitely are well-proved methods that do work, so we'll probably look more into that once we get started in the cam. We'd be using the ST30 SSY. Again, no fixture plate needed, so that makes things a lot easier. And yeah, we'll be doing the cam very soon. I've said it once, I'll say it again. We should have the cam done within the first 2 weeks of C term. That's our goal. Thank you for your time. Do you have any questions?
I know Matt said you had a lot of questions, right?
I just had one. Where it was slide 13, you don't have to go back. Just when we were talking about the margins for the wedding cake calculations, you mentioned you could use like bigger washers. Is there space for bigger washers?
Slightly.
Okay, but like enough that you could do.
Like, does a washer exist that's
I don't know. There's still space between the edge of the plate and the inside of the tail cone because they added that shoulder on the bottom of it. So we do have like a little bit of room to play with. I don't know what the exact sizing of washers is. Like we're using ones that fit right now, but.
I don't know. All right. So for the Payload Slide 6.
It's okay. Oh. Almost. Yeah. Might need a second. All right. This should be. There we go. Right? Okay.
Oh my God. Okay. So note the radial bolts for tail cone are very
Yeah.
material there.
Yeah, this was a very last minute addition. Yeah, I think for the future, we're going to look at decreasing the thickness of that lip that the axial bolts go through. Yeah, and then adding the radial bolt holes on the, yeah.
Okay. That's fine. I did like the wedding cake one had a lot more space.
Yeah, no, yeah, I agree.
Um. Okay, that's another.
13. I swear 2 more are coming. Oh, no, there we go.
Okay.
Yeah.
Are those paths required? Just curious, why the paths are already in metric students?
Yeah.
Why are we using?
We don't need to. When we were initially finding CAD for standoffs, we ended up using M4 standoffs. So then all of the bolts are also M4. We can not do that.
If we don't do that, it's a lot easier to find new screws that I have.
Yeah.
Use metric screws, it's a very good chance no one will.
There's international teams.
They also use Imperial.
Let's go. That's what we found. We can find ones that aren't that. That's fine.
Make them Imperial. We all know that you make Imperial already. So, I was like, there's no, I was trying to assemble a 3D printer today. I'm like, there's no screw exactly where that fits this all. I was like, I don't know what this is supposed to be. I had to tap the 3D printer. Okay, for the slide 14. Okay, if to me it looks like since the fact that it's kind of high still, like you probably could shrink the size of those tabs that come out.
Okay.
That seems like a nice spot, likely. It's small, but like, me, it doesn't seem like there's any reason for them to be as big as they are.
Okay.
Quite thick, or like what you have on
Mhm.
Thickness and radius, or just thickness?
If you change the radius, the screw head probably not, will stick off the side, so my guess for you is the only difference. But if you're looking to change the radius. My first thought was just the thickness seems like they're reflecting what they're doing. But I don't know, it's also big motor, so just keep that in mind. And then slide 17.
Here we go.
Yeah, what is the actual difference in weight? You know?
I believe the aero pack's half a pound and the plate is quarter of a pound.
Yeah.
Oh, yeah.
Mhm.
All right. Just curious. Thank you. That's all I have.
Yep.
Like within what, because like, it's right, there's some margin there. Ask that. Yeah. So I think the deal was, yeah. And the other speaker. So we can put the speaker. Okay, it's one thing, sir. So, we should do this. I'll talk about that.
Theoretically, actually.
Like how you're. I said, you know, it's coming to shower. Yeah. Yeah. Showed up with his work. Walk in the shower.
I mean, we have it.
Email.
Yeah.
That's actually just what we. This one is, we've updated this.
Is it? I don't know, way though.
What have you updated?
Those are very.
This way is a lot obscure, and they're also.
This is the one.
Okay.
So it should be.
No, it's not. That's the only day. So they had.
As in, say, I are
I like this more three metal. That's like a.
Yeah, I think that's what happened.
I've only gone there right first.
Well,
Yeah.
And then it's just like, go with this, no one like. Oh, really?
Just, well, it's actually against the law.
Also.
Yeah. Oh, yes, I did.
Can't break the. Last.
Oh, okay, I was just saying. This is the one that you have.
This one was used. This is not what's good. And like. So why do everybody pay here? There's genuinely this one, there's also fun. Well, it's I'm sure thing about like it's not in terms of mine, like there's this one I agree is a little more top down. This one was if it's switched buttons. But it's not I think it's like if it's just yeah, it's yeah, I know it's the one to do the one.
Yeah.
Everybody. Are these getting, are the questions getting written down somewhere?
Yeah.
Just for your, just for your presentation. You guys actually,
No.
they're on YouTube. They're on YouTube.
You put them on YouTube?
Yes, all that. We're gonna really tell everyone. Yeah, there's someone who's trying to get the 632 screws into it. I'm like, I'm gonna not get a screw in the 632 screws. Well, yeah. Just about to show them.
I like beverages.
You gained one. Happy holidays. Oh, that the right one's your bad. So he was. I could.
What's in the I don't know, it's like winter ones. I don't know what the actual flavor is. So like, the only slides.
I did too, and I once spoke. Baby dragons. Baby dragons. Yeah, don't not like my tombstone's level 10. I'm the master in tombstone. I only ask for tombstone. It's great. Have you seen my account? That's my little power guns. I'm really not used. Are you? I'm like an old. Yeah. Oh no. Every card I have. Oh no. This season I'm gonna pretty much run my friends. Yeah, they're probably actually trying to get top five. Yes. I'm trying to do sometimes. That's right.
For some reason, everybody's bad.
Okay, well, how come?
What about that?
I was looking at it today.
Well, you're acting like they were earning more advice. Like 10 years, yeah. Like you say, I'm going to stand up. I didn't love that. I really draft that. Because there's something we keep dragging that out. It was all this for a direction. Not really, like I did my day. Nice to meet you. Okay, all right. Alright, let's stop here. I don't know.
You guys have like 5 minutes left.
Hey, better early than never, okay?
Take a photo.
We do have to take a photo.
That's my lower level.
I don't know if everyone's here, though.
So. I don't know.
Jordan is not.
Michael, I think I'm donating. Who is donating to?
Your plans. I got
Yeah.
Jaden, you're presenting.
Yeah, picture first, guys, picture.
If you want. Sure. It's fine.
Wow, you guys look so cohesive, got a cohesive color scheme going on.
That was totally planned.
Yeah, you wanna switch, stay.
Like, a little bit, 1 like 20. Yeah? You haven't played me yet.
Smile if you like HPRC.
Yeah.
Aren't you so excited to be here?
That's
Because I like church.
People will love you. You know what
It's our captain right there. Bigger fidget.
Oh, no, I was definitely straight. Trust me.
I just hate it, and then I did it as well.
Are you like rotating in between them or do you work on one of them? How to keep it very.
No, we planned this.
We planned it.
Really?
Oh, something you want to say?
Yeah. When I click right back here.
He knows. Dude, you think? Oh yeah. In the middle of this, can we have. I like that thinking, man.
Whatever.
Oh, she's fucking comfortable. What do you mean they're uncomfortable? I've worn a dress shirt on this.
And Jensen went like 90% of the way to a suit.
And then just couldn't, they didn't throw the jacket on. Couldn't be bothered.
Almost there. It's a cheap-ish watch. Sunset Sunday this week.
It's gonna be up. Are you guys ready? So when you present, you just make sure you're kind of like within this sort of line, otherwise the camera can't see.
All right, we good?
Let's start. Punch.
All right, welcome, everyone. We're the 30K Rocket Recovery Team. This is our CDR presentation. I'm Jensen.
I'm Matthew.
I'm Harry.
I'm Diana.
I'm Jade.
I'm Jemiah.
A little bit of a system overview. We have our dual end, dual deploy recovery and avionics bay. It's a CO2 black powder hybrid ejection system, and we have 3 subsystems. We have our parachutes and shock cords. We have our avionics systems and mounts, and we have our recovery sled. Some basic information about each of them can be seen on the screen here, and we'll go more in depth later. So our timeline, so this B term, we have obviously our PDR. We wanted to finalize our CAD, finalize our simulations and calculations, do some wiring diagrams, and obviously we have our CDR. Next term, we're looking into getting into our 3D printing prototypes, test assemblies, wiring harnesses, and ejection testing and altimeter testing.
I'm Harry. I did the parachutes and shock cords. For requirements, we had the shock cords retain integrity, drogue deploys at apogee with the descent rate of 65 to 131 feet per second, and main deploys at about 1,500 feet with a descent rate of less than 36 feet per second. Current specs are the shock cords retain integrity, drogue deploys at about 27,000 feet, descent rate is approximately 80 feet per second, and main deploys about 1,000 feet, descent rate of 22.2 feet per second. This is the basic flight diagram. The numbers from Open Rocket from today. It's the last updated today. So I can get to the next slide. This is the main parachute that we're going to be using. It's a 96-inch toroidal shaped parachute, so it's like shaped like a half of a donut. Has a descent rate of 22.2 feet per second, opening force of 104.41 pounds, opening time of 1.44 seconds. It weighs 25 ounces. Packing dimensions are 4.9 inches by 7.4. We're going to decide between the 2-stage recovery team whether or not we're going to reuse these parachutes from last year or give them to them and buy new ones for us. Choosing this because the central hole and ring shape create a stable wake and reduce oscillations, and it's the one we used last year. Has a coefficient of drag of 2.2. And this is our drogue parachute, 36-inch elliptical parachute. Opening force 23.59 pounds. Opening time is 0.15 seconds. It weighs 4.46 ounces. Same thing with the other one. We're going to decide whether or not we're going to reuse it or buy new ones. Has a coefficient of drag of 1.5 to 1.6. This is our pre-launch configuration. This is the current line diagrams. We added 12 inches between the lower and middle airframe to account for the shroud lines. Used a MATLAB script to make sure the geometry works out so that nothing hits each other when the main deploys and the drogue deploys. And we're going to use nylon shock cords for both the main and drogue shock cords. That's what we've done in the past, and we're no longer running the coax cable along the drogue cord. And we're going to look into, during C-term, what we have currently, and so what we can reuse and what we'll have to buy.
Hello, I'm Jemiah, but you guys know me as Maya.
Matt.
So the requirements for our avionics team is dual and deployment, completely redundant altimeters, so basically having 2 of them. They're both usable above 30,000 feet, 20 minutes of data per flight. And we'll be working with 3 different cameras, outward facing, drogue facing, and downward facing. So we wanted to also streamline the downward facing camera mount. And also no LiPo batteries this year because they don't work well. So our primary altimeter that we know and love is the Blue Raven. It's been proven to work throughout all the years, and during the test launch last time, proved to work really well, and we got very useful data. It's from Featherweight Altimeters, and it's also Bluetooth and micro USB interface, so it works very well with everything else. The redundant altimeter that we chose is the RRC3 Plus. It's by Missile-Works, so it's a different altimeter, or a different company, I should say. And so if there's any issues with it, we have a different manufacturer to fall back on. Our camera systems is, for our downward facing, is the RunCam Split V4. And for our outward and drogue cameras is the RunCam Robin 3 and the RunCam Phoenix 2 Nano. We're running with all three cameras, we're running with the same company, RunCam. And they're all very affordable, with the Robin 3 being $15. So great for our budget and great for our system.
So this is our outward camera mount. So this is going to be 3D printed and mounted onto the side of the sled. And this will just be pointed outward. And so you can see the mounting on the right. This is our drogue camera mount. This will be mounted onto the bulkhead and be pointed outwards, looking at the drogue. And so after we mount it onto the bulkhead, we'll seal it. And you can see the mount with the camera on the right.
Right. This is our streamlined camera mount for the camera that's going to be coming out of the side of the switch band at an angle to give us another view. It's going to be mounted directly to the switch band. As of right now, it bolts onto a mount that will be placed on the inside. We might be looking at adjustments in that in the future. I'll be using 632 bolts. Has a relatively minimal footprint, so it will not impact the flight of the rocket all that much. We did run a simulation on the mount itself. It got a low drag coefficient about 0.1. We ran that assuming that we were hitting about Mach 1.4. In the open rocket simulation, we're now hitting about 1.7, so we will be rerunning that, but we're not expecting a major change. This is the wiring diagram for the sled. Again, we'll be using the Blue Raven as a primary and the RRC3 Plus as the backup, with the power from the batteries being wired to the screw switches, which are located around the switch band as well. Yeah.
I'm Diane.
I'm Jaden.
For the requirements, we wanted a redundant system. We wanted to CAD the entire sled in on shape so that it could fit the 5-inch ID airframe with room for all the avionics, and that it could also hold the CO2 ejection system. For the bulkheads, once again, we wanted it to hold a CO2 system, withstand the opening forces, and have a lightweight fiberglass design with a flange. For the bulkheads, we wanted to use the G10 fiberglass and have a flange for a coupler to help seal it off. And we have a bulkhead for the black powder and a CO2 variant. For the black powder bulkhead, we ran a simulation on ANSYS. We were able to get a factor of safety of 4.73, so it's safe. And we used an opening force from the main, which I believe was about 104 pound forces. We also ran it through SolidWorks FOS simulation using the SciWu criterion for failure. We were able to get a minimum factor of safety of 10.763. For the drogue bulkhead, we once again ran it through an ANSYS simulation. We were able to get a really high factor of safety of 18.62. And we also ran it through SolidWorks, and we were able to get a minimum factor of safety of 41.49, so very high.
So for our sled, It's a polycarbonate sled and it'll be 13.5 inches in length. As we mentioned, we do have redundant electronics for like our altimeters. We have multiple mounting sides. We'll be using the black powder bulkhead for main and then the CO2 for the drogue. We also will have access to the screw switches through the switch band. So everything is held together with 1/4-inch threaded rods that will be going through the whole sled, and it'll compress the bulkheads onto the coupler tube. The sled has Mars and radio board mounts, and we'll be running the wires along the rod channels. So moving forward, we'll have to make a prototype sled along with practicing the assembly of the sled. We'll do some vacuum chamber testing for the altimeters, wind tunnel testing for camera mounts, and then ejection system testing and ensuring proper wiring of the sled. Any questions?
I have one question on the simulation.
Yes.
Not that it matters, it's obviously failed.
Mhm.
Okay, but for the side move, then did you do 3D or
2D.
that's good? Like and for this specific case, then the load's gonna be out of plane, this pulling like
Okay.
uh,
No, I think it was 3D. Sorry, it was 3D, not 2D. Okay. Yeah.
just like the 1 and 2.
Yeah.
Pulling
It'd be pulling along the 3 direction. Yeah. So yeah, it was 3D. Sorry.
I don't know, but what do you think affects the factor of safety being different cases?
I can talk about this a bit. So these were both done in SolidWorks, not ANSYS. The von Mises stress simulation is it's an approximation because it's a composite. So von Mises doesn't really work for failure criteria because composites are stronger in different directions depending on what direction the force is acting in. So initially we had the von Mises stress simulation and we calculated the factor of safety using the lowest tensile strength for the bulkhead. And we got these factor of safeties, not too off from what I would consider it to be, considering our PDR simulations as well. But we also used the Psi-Wu criterion for failure in SolidWorks. This was a little bit weird to set up, but it's more accurate and it takes into account the strength in different directions for composite materials. And we got a higher factor of safety for this, also not too off from what I would expect. So.
No other questions? Sure, mine are silly. The first one is, have you considered colors for your parachutes?
No, but we can choose anything probably.
Also, this isn't like so much of a comment, but I know that you think you've accounted for shroud line lengths. But I'm not saying you haven't done a lot of measuring and calculations and all of that. I just really want to make sure we do full testing as soon as we can. If we have the right size parachutes, then using any airframe just to make sure that it clears it.
Yes, we'll do that in the C term. And we'll also cut the lines probably in D term to measure them out and make sure they're
Every time you get more of the system, do another test. Do a lot of them. Last thing is for the recovery slides, slide number 45. Something that I think we should have done last year, which I don't see, is a clocking feature so that you know the switch band is. Exactly.
We'll have a bit of a clocking feature with the outward camera mount. I don't know if there's a good, probably in sled. You can kind of see how it is almost like a square that we would cut out. So it'd be like a ring with a, yeah. So it's kind of a clocking feature. So that should help align stuff, but.
I just have a quick question. I wasn't here for your PR, but I was just curious how the CO2 furnace work.
Yeah, they do use a little bit of black powder completely sealed off in the actual mechanism, but it basically fires a spring-loaded, almost like a sharp point into a CO2 canister that ejects the CO2. So.
And that goes through the holes that I saw on the other side.
Yeah, like oh, that's not good.
It's just an interesting looking.
Yeah, like you can see the little holes at the top outside, like the little gray thing on the CO2. Yeah, they go through there.
Okay. Is there going to be anything that's going to sensor the camera?
Where is that? That's avionics problem.
Yeah, that one.
What were you looking at?
So, I know I put it in thinking, that is not. But
Mhm.
you might want to put some sort of like, the answer,
Okay. Yeah, we can look into that. I mean, it wouldn't be too hard. Just cut out a little thing on the other side of the bulkhead to put plexiglass in front.
And then we could theoretically seal that off. And screw it in.
That would save us some time for that. So yeah, we'll look into that.
And that'll be sealed, right?
Yeah, it'll be sealed.
Have you looked at all, like, I mean, we've done the taps, right? Like the camera there. Like, so I'm just thinking, like, do we know what kind of view we're gonna get? I'm looking at the.
Sorry, I missed it. Sorry, I missed it. Payload had a similar.
Right, and it was like a similar setup. I just want to make sure we're not putting this here. There's going to be a bunch of things. So to make sure it's worth your effort.
No, I mean, there shouldn't be anything in the way other than the parachute.
Right.
And the parachute, once it's deployed, we can also like test it. You know, we just hook it up and see.
Yeah, pretty easy to.
Well, it wouldn't be on that side, so no. Yeah, especially if we add like the plexiglass option, it'll just be. No, it'd be on the bottom side of the. Okay.
Just to verify for the simulation, in metric, you guys converted to velocity, right?
Yeah.
It's on slide 44. Just want to make sure that it is outputting metrics, so I just want to make sure that's what it is.
Yeah, no, because everything in the simulation was in metrics. So yeah.
So that's also on that.
I was going to ask, when you did the CFD, I just want to make sure you did it with compressible flow.
Yeah,
Okay.
obviously because it's mock. Yeah.
Did you like trust the when it was in?
No, I mean, there's a lot of things about this camera mount that we're probably going to change. One, for example, like material wise, if we 3D print it, I'm not sure how that's going to hold up under thermal loads when we're moving this fast. Typically, camera mounts are made of like nylon or like Delrin.
Well, I'm more concerned with the layer lines are going to cost.
Yeah. Mhm. Yeah.
Something we could do. Yeah, but it's still gonna. What we should look into is to make sure it does have a tiny thing. No, not resin. An former. They have a vacuum former in the main space.
Oh, okay.
Some sort of plastic over top of it, and then we get that sort of it.
Okay, yeah, we can definitely look into that.
So we can look in,
Mhm.
and I'm pretty sure it's just happening. It's still there. It is. I mean, it was there. Yeah. Like that.
I have no clue if it's there or not.
Cool. If they do have it there, I know you just like trading it.
Okay, cool.
Yeah. We can.
So for the one altimeter. For the Blue Raven, it says that, so the battery is a 16-volt pack. I mean, I know that the slide says, like, well, I know that's just like the specs they're given. Does that mean that we need 16 volts?
For the, no, we're just gonna use the batteries we used in previous years. So like the 18350. Yeah.
They just have 16. Well, that's what I knew. Yeah.
Do we have the battery somewhere?
I was looking on slide 38. Where it says 16.
Oh, I should look for information how.
I know that the specifications that like they give on the website.
Mhm.
Like, I know sometimes they throw out like different voltages.
Yeah. Yeah, let's say we should. Yeah, we don't way more than we need.
Let's do for the drone and the outward-looking cameras, is there any reason why you chose two different models?
Those it's either or. So like
But
right now, yeah, right now the sled is configured for basically 3 live video cameras because the dimensions for the boards the other 2 need is very unclear on OneCam's website. So the plan, at least I had, was just to order them over winter break and then change the mount slightly once we actually see what it's like and take actual measurements of it. But yeah, it's like either or. We can look into, they both should work fine, but we can like look into comparing them over winter break and just say, we'll choose this one because why not?
I was just when I looked at that, I thought you were saying that like you were
No, yeah, it's like
one place and the other one.
Yeah, it's just either or.
Okay. And then for the live video stuff, I know we talked about in PDR about what assembly would look like, taking the camera out. Have you thought any more about that? Because I know the wire for the live video camera maybe wasn't quite as flexible as you thought it was going to be.
Yeah, I don't know.
Well, maybe I'm wrong.
It's decently flexible. I mean, it's a little hard to see on the sled, but the board for it is directly below the mount, so there's not like length of wire isn't really a concern. This doesn't show it unfortunately, but the screws go into the side of the camera here. They're like.
Okay. So we can just take that out.
Yeah, you can. The idea was just to put that in initially before like the whole bay, and then put the whole bay around it. So
when we bought the OneCam, the cord was a loose cord. It was flexible.
And then you're envisioning, so like for assembly, the camera would just go in like first, and then
well, that's another thing because. I don't know. Nick, were you able to Wago the wire for the live video properly? Or like you cut it, didn't you cut one up for the avionics bay for the lift launch? Oh, okay. 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 That could probably work for assembly. There also is, for this camera mount, this was the idea that we had from PDR with Ground Station, have it angled like this. There is, and what a lot of other people have done is they've taken the mount or the camera and moved it completely to the outside of the rocket, so it sit like vertically down. It's just a matter of how much we're willing to sacrifice for drag, and if we want to induce a moment on the rocket would be a concern. But it probably like something like that might be easier to assemble just because you could put the bay and stick the rocket basically out the little hole and then just screw it in from the outside there. So
yeah, I was just thinking like, I'm not, because I'm also thinking like for day of, what would be really nice for a day of checklist is to be able to like test the remotely starting and make sure it's recording, and then like look at the SD card, make sure it's recording. But once it's assembled,
yeah, you probably won't.
And that's fine. That's fine. I was just curious. Oh, you're right. We can't. Yeah, you're right. That's something to figure out later. I was just curious if you thought about that. That sounds good. I guess recycling is nice to do that. And then I also have some questions on slide 54, just for the sled. Well, I guess slide 53 and 54. Is there a mount for the GPS antenna?
The one that goes in Mars board?
Yes.
Right, it's kind of hard to see. Right next to the. I took that from the dimensions of that. I think that's what you're talking about. It was like.
There's the radio board. So the radio board's blue, right?
Yeah, and then right next to the radio board on the left is like a spot 4, I think what you're talking about.
That's
Yeah, I don't know if it has to, on the avionics bay, it has to be, you guys have it as a angle, like angled slightly. I don't know if that's necessary, but.
It's like a patch antenna, so it'll like be best to the direction it's facing.
Okay.
So like most satellites are typically up. So if we can get it like angled, that would be great.
I can look into that, but
Okay.
yeah.
I mean, it's probably not the end of the world if it's not, but.
Yes, I mean, we would probably have to like put it on the inside of the bay almost then if we wanted to angle it, like on the inner wall, if that makes any sense.
Yeah.
But,
And it's a matter of like, is that actually worse?
yeah, if there's stuff in it, yeah, so.
Okay, and then the other thing, I was looking at the distance between the transmitter. I assume the little nub coming off the top of the transmitter is.
Yeah, it's lifted up. Yeah.
And there's also the other SMA. Maybe it's just like the perspective. They look really close.
Yeah, no, there's clearance there,
There's
so.
Like sideways.
Yeah, it's just bad
Yeah,
perspective.
it's just a perspective. Yeah. And then do we have a wiring diagram for the Mars board?
Not yet.
I mean, maybe that's something that you should do.
Yeah, I mean.
And that's fine. I was just curious.
Say like, I don't really know
Yeah.
what they're planning on doing for wiring stuff together for the Mars board and radio boards. But
Yeah, but I know the batteries you spec.
yeah, say
Board.
we can. Yeah, we can hold like probably can hold way more batteries than we need to. Like we have 9 on there, and I kind of just like, okay, that's how many we can hold maximum. We can take off some, and it doesn't matter. So.
Well, ideally, some of those might be able to be 1850s instead of.
Yeah,
60s.
yeah, looking into that as well. Especially for things like the tele GPS, might be able to use an 18350. I think. Sean, do you think? Yeah. So.
If we're a multi-startup.
Yeah.
Another question, we were talking yesterday with two-stage mechanisms about like what's the equivalent of the purple like standoffs for the antennas? What are those planning on being made out of?
Some type of flexible material to avoid damaging the boards. So like TPU or something, 3D printed.
I was actually use sauce. Like some burn, definitely saw.
Okay.
That was the same.
It's like, okay. I mean,
I'm trying to figure out who told y'all that last year.
I don't know. The standoffs can be made of anything. It's just a material. Like, okay. So that'll work.
Yeah, we can buy that.
Mm.
Yeah, no, it's totally fine. I was just curious because we talked about it too. And what does assembly look like? Just because of the fact, like in the past, the altimeters and the avionics bay have been separate, so they can like flight software electronic, the ground station can do whatever they need.
Yeah.
The entire bay because
Yeah.
they're separate. Like, what does assembly look like on day of? And like, have you thought at all about like if recovery's trying to set things up at the same time that E&P needs to be doing other things?
Yeah. Haven't given as much thought to that right now, but what I'd imagine is we get everything set up outside of the batteries the day before. So that way recovery can basically just put the batteries in. We can probably make the charges. It's like we can make the charges for at least black powder separate from everything. We also probably can do the CO2 charges separate while EMP works on the boards. So.
Oh, there was a little bit less setup.
Like,
Yeah.
theoretically, the mark would already be on there.
It should be.
Mhm.
Yeah. Well, what I'm saying, like, if we're doing any testing, and I'm not saying we're gonna take the basic, I just want to
Yeah.
make sure there's no like conflict.
Yeah, no, it should be fine.
Okay. Yeah, no, I agree, and we'll figure this out later. I just wanted to know, does that sound what you have?
Questions?
So we are Payload Actuation. My name is Steve.
My name is Justice.
I'm Aisha.
I'm Nate.
And first, we're going to start off with our sub-team goals. Our goals for payload actuation is to creating a release mechanism that is able to withstand the force of ejection and parachute deployment for the rover, as well as developing an efficient system to withstand the forces, creating an efficient system in order to actuate the antenna. This is our timeline for the year. In A term, we mostly focused on developing and brainstorming ideas and basically early development of CAD. And B term, we refined CAD as well as printed some 3D printed parts. C term, we plan on finalizing the CAD as well as doing some stress analysis testing. And D term, we plan on integrating our entire system with the rest of Payload, as well as creating our ready checklist. In our first section, we're going to talk about our release mechanism.
So the release mechanism has been updated from being a door that held the rover in the payload to now being a latch mechanism that holds on to the rover itself. This system will be completely behind the rover with nothing beside it or in front of it like the previous system had. The latch will be mounted to the top cross member with the latch release mechanism mounted to the bottom cross member. And the latch will interface with a handle placed on the back of the rover. Looking closer at the latch mechanism, we can see here that there are two standoffs that are screwed to the top cross member. These standoffs will act as guides and constraints for two springs, which will push down with 1.8 pounds of force on the rover handle. The handle will be attached to the rover with two stainless steel lock nuts. Looking at the release mechanism, we can see that there will be a 3D printed servo horn shaped like an egg used to release the latch. There will also be a 3D printed servo holder, which will be screwed and mounted to the bottom cross member.
Moving on to the release process. So when the rover is first inserted into the payload, the spring plate will be pushed upwards, and once the rover is fully inside of the payload, the servo will be rotated in the opposite direction of the arrow, and this will allow for the rover to be kept in place. As the rover exits the payload, the servo will rotate the servo horn upwards in the direction of the arrow, and this will push the plate containing the springs upwards and compress them, and this will allow for the full release of the rover from the payload.
Now is on to our servo selection. In order to compress the springs, we had to develop a servo that was strong enough in order to meet the required torque of 76 ounce-inches. And the servo we chose was the RS 100 high torque micro servo. And this servo is a very powerful servo. It can output a torque. It has the available torque of 100, has a stall torque of 174 ounce-inches, which is well within our safety factor of 76 ounce-inches for the torque required for the springs. Now it's on to the force distribution on the system. So you can see by the red arrow, this is the direction the rover wants to go when the parachute is deployed, and it's going to go directly it's going to directly influence the metal bar that runs through, or the aluminum 6061 bar that runs through across both cross members. And this is the area of contact between 2 points we mainly focused on. The handle, which is the surface area of the handle that contacts the metal bar, and then the surface area of the bar when it contacts the cross members. Here is the calculator I used in order to figure out the compressive force. The compressive force that would act on the handle component that I mentioned in the previous slide. And based off this calculation, if we assume that it was made out of PETG, it was 0.004 of deformation, which is well within the tolerance of 0.04. We plan on testing the system out of PETG first, just to make sure that the calculator is correct. And if not, we have plans to develop this system out of aluminum 6061 if it's necessary. And here's the calculator we used in order for the contact area between the bar and the cross members. Since both parts are 6061, this is the compressive force that would be acting on the bar. And we can see that the deformation from this force, or this stress, was 0.009 of millimeters of deformation, which is well within the tolerance of our of aluminum, which is 0.12. And for our ejection force distribution, we're going to reuse the system from last year, which had a 3D printed component before the payload. And what this component allows, what the goal of this 3D printed component is that it distributes the load evenly through the L channels and to the top cross members. And this is just a system that we plan on. This is the system that we plan on using again in order for absorbing that ejection load during apogee when the payload separates from the rocket. And finally, and then the image to the left is rover's design in order to mitigate the sand coming into the system during crash landing. And this is kind of their system, or their system to not allow too much sand to get into the sensitive motors. And now we're going to talk about antenna actuation.
For the antenna actuation, we will have the antenna. It'll be wrapped around the bottom like a coil, which will then be glued onto a 3D printed servo horn mount, which will be attached to a cut servo horn into a servo. And the servo will be then attached to a 3D printed mount that goes in the rover. We're planning on using glue to hold the coiled antenna to the 3D printed part. We talk with EMP, and glue shouldn't impact the antenna's efficiency or capable of doing its job. For the actual system, we'll have a coaxial cable that'll be wrapped around the end of the antenna, closest to that 3D printed part. It'll then be soldered onto the metal plate, which then can feed down into the Mars board. For the actual mounting onto the rover, we're using 632 screws to mount the metal plate onto two different 3D printed parts that'll be mounted onto the rover individually. The metal plate is sat right above the rover, so it shouldn't interfere with any rover mechanisms, while also giving enough space to attach electronics to the Mars board. And the antenna sits above the metal plate, and that even though it hangs over the edge of the rover, that fits in between the top cross member and the latch mechanism, so there shouldn't be any interference. For mounting the antenna and the parts we chose a 9-gram micro servo because we're not expecting a large force just to lift the antenna and hold it upwards. So we picked the small servo we could find that would have the allowable torque. To mount the metal plate and everything into the rover, we chose to use brass 632 heat set inserts with 632 flathead hex screws to attach all the components together.
So that's our presentation. What questions do you guys have?
What is the reasoning for the X shape of
The X shape?
that is like arbitrary taken or?
The reason for it was just, I think that was just if you want to touch on that, just this.
We needed a servo horn attachment that could go from a horizontal position to an upright position in the most efficient manner for space. And that's the shape that we landed on. Yes, correct.
Then with you say you want to use like a 1.8, it's on set 62. The 1.8, I think with the spring, that number, like, how did you land?
So the spring constant for both of the springs is 3 pounds force inches.
Yeah.
And we need to raise both of the springs 0.3 inches up to release the rover. So I multiplied the spring constant by the distance traveled and by 2, got the spring force.
So you could theoretically use a higher force spring.
We could absolutely use a higher force spring, but we don't expect any force from the rover to be pushed up. So
Yeah, that made me sort of, did you calculate for any like preload force, just enough to like mobilize down a bit?
Yeah, that came to, so currently there is some the current idea is there is some like pre-force from the string that is actually pushing it downwards. It's not currently on the slides, but yeah.
The piston, you guys think that? Or is that?
That's payload recovery.
Gotcha, sure. They should have.
Yeah, they were mentioning that. Okay.
And then, so if you were to like the first slide we showed the system, it would.
Mm-hmm.
For this one. So is the blue part like? I'm gonna be misunderstanding from this book.
Yeah.
Is the blue part, does it have like a cutout in it so that it like goes over the latch? Because like, I know the latch itself on the rover is like an L, right?
Mhm.
And so how is the cam actually getting to the latch and push it up? Is it like where there's like a rectangle and then there's a slot in it, so that goes to the latch and the cam can also push it up, or is it just straight up a flat?
Which part are you talking? Like which color part?
Do besides you.
we have a sideways view at the very beginning.
In the beginning?
Yeah, we have a complete.
Yeah, but so I'm saying, does the blue piece have like a slot in it and that's what's going to watch?
This part?
The top, like the actual that pushed it down.
Oh yeah, there's
like a slot in it.
there's it's screwed on. It's there's screw. Screw. Does that answer the question? Are you saying like how does the bar?
Like how is the bar getting over there?
It's just being pushed upwards. At this.
Like for essentially.
Like
I think I'm just looking at it. Okay. I have people ask questions about it.
Yeah. Oh, have you done FBA on the gray or the white piece of the latch?
We have not.
Okay.
Yeah.
That would be cool to see, just like the force.
Also, yeah.
Right now,
Like the light.
We want to test it 3D printed and we,
A lot of force
yeah.
onto that.
yeah.
Mhm. It could be, yeah. Especially if we have the space for it, or I mean, the weight for it, we can definitely have a machine.
Oh, and also, have you thought about doing where those two faces meet an angle so that we could kind of just push the rover in and it would like snap?
Yeah, we thought of that design. The main issue with that would give us less surface area in order for the handle, so it might weaken that part. So that's something that we want to avoid.
Based on this particular slide. One of them being in terms of tolerances of the latch, which is that handle.
Mhm.
I just want to clarify, first of all, that they're not touching right here, and this is when it's like being held in place, that the handle's definitely not touching. There's space between them, so the forces are only on.
Mhm.
Let's see this. So it's just holding it this way. There's no force pressing down on that handle, right?
You mean like these two components are?
Yeah.
Okay.
So sorry, I'm just going based on what was.
Yeah, can you repeat the question? I guess, sorry.
So I have two tolerances.
Yeah.
This one is, it's right now, it's not that dark gray block.
Yeah,
It's not touching the handle, the L shape, right?
it should.
It's only touching on the side.
It's only touching it on, it's touching it on the bottom and the sides currently.
So it's pushing down on that.
It's pushing down, yes.
So how sure that that's not gonna tip things? Like,
Tip things like, yeah, like tip the payload from,
I don't know if that's actually an issue. I just would be hesitant if that is making contact with the bottom of the handle.
Mhm.
Like, we know what's happening.
Okay, yeah.
The other tolerance question I have is when the egg shape is being rotated.
Yep.
Assuming that it rotates fully and the latch goes up.
Yep.
Actually, some questions related to this. The first thing is, what are the tolerances on, how sure are we that the latch is not going to catch on the handle? How sure are we that it's going to be able to, how far up does it push the handle?
We have, yeah, there's currently some room. There's like enough. That's kind of hard to say. Right. Yeah.
Okay. So that being said, what happens if the servo? Okay. Maybe I'll start with one. I'll show you that the 3D printed egg shape is going to be able to. I guess, like, have you put any thought into the material and how well it's going to be withstanding forces from that 1.8 pounds of pressure down, but also the torque being turned? Like, what's it being attached to the servo?
Just like the, are you saying like for the actual like structure, like for this component, if it would break, or, like where's the point of, like, for example?
Yeah, I guess just have we considered the forces that are being applied to it and what?
Yeah, we have, that's something that we would have to design, I mean, account for. I think for the selection of the material, I think what we have right now is that it's petchy, and we would just increase the thickness of that part to increase the shrink. And we'll kind of just like iterate on that.
So it's about it should serve on that point of connection.
Mhm.
I'm sure that isn't gonna like shear. Sorry.
It's a metal.
So it's just like holding it in place with a screw.
Actually, yes, there's a, you know, on servos, there's like a 25 screw. It's one of those.
So it's like slot.
Yes. Oh, you're talking about the, okay. Oh, yeah, it's slotted in place, yeah.
I would be worried, at least in the cabin, it's kind of like all the way up.
Mhm.
The arm is 90 degrees.
Yeah.
And that gives you basically no force upwards.
Okay.
Same amount of torque. So the closer you keep the arm to vertical,
Yeah.
the more force you'll be able to get.
Okay.
So
So
I think it's good, but if you just
increase the
like
length.
lift the servo up more,
Okay.
then you wouldn't have to make the arm any longer. You can get the short maybe.
Yeah.
And then you get more force.
Okay. You can definitely improve on that.
The pad has a circular shape on display, but it's not circular.
Yeah.
It's gonna have to, the CAD just doesn't have that yet.
Yeah, it doesn't have that, yeah.
Another question is, what happens if the servo, we have like stops on it, or what happens if the servo turns too much? Like rotates the egg past, because it's rounded,
Mhm.
if it keeps going,
It would hit.
it would drop back down, would it?
I think how like just servos work, they have like certain amount, or at least position servos, they have like the fixed amount of like force that would stop it from going backwards. Or
Well,
yeah.
I don't mean the servo rotating backwards, I mean it rotates forwards more than it needs to.
Mhm.
Like, is there?
Yeah.
Is a position control servo?
Okay, so you're just setting the position.
Yeah, we're saying, yeah.
How did you calculate the torque you need for that servo?
It was based off just the spring constant, just like the force applied, and then just the basically the lever arm from the distance between the point of contact from the most compressed position to the head of the servo. Yeah.
And have you put any thought into like, well, I guess, so what are that egg is 3D printed?
Yes.
I'm just thinking like, if you do a lot of tests, is there any thought about like those surfaces rubbing getting worn down over time? I mean, I know there's like, if you're pushing it up pretty high speed, if they get worn down,
yeah,
there's still space, but.
There was, yeah, for like wear and tear and like sustainability. I would say that wasn't a concern with that wasn't like a thought process, like concern we had, because the system will only be tested once. I mean, would only be like working once. So yeah, I don't think that's too much of a concern.
I'm just thinking.
Yeah, I just print a new one.
Yeah, I was gonna say, because I mean, ideally we can do a lot of tests with this, so maybe
Yeah.
when you go to IREC, you can have like a new pair that has been tested and then.
Yeah, that's fair.
I was gonna also say, just make sure you print it out as something that is heat resistant.
Okay.
Because if it like softens in the heat, then.
Okay. You might want to move here something. But if the cabin is vertical, the egg is moved to the left spring.
Okay.
But if I have some binding issues, they just try to do that last bit. It's going to be pushing a lot more than what's on the side. I know they can't really. This might come from like storm, the shorter center. So I think. It looks like it might mark it up a little bit. Just trying to get it up. Yeah, especially if it's like, because it's pretty far to the left. And the other thing too is, I see now about how the underworks. I'm just, what was the reasoning? I think it comes out of two different pieces, like the stop block that goes into the hook, and the piece that actually holds it onto the spring.
You mean just these two parts?
Yeah, why are this?
Mostly just because, I mean, we could machine it out of just one part, but or 3D print it, yeah, just to test it. I mean, that was the idea. I mean, if we were gonna machine, it was mostly just due to the fact that we would have to machine the bar, and then the blue piece could be 3D printed, and because it's not gonna, yeah, or
I see saying.
Yeah.
Definitely, I like this idea a lot. I think this is a lot less better.
Okay.
I definitely like, I see you guys. So start to test stuff. So you're gonna have to. I think the egg shape is my guess would be the egg shape is more conventional.
Okay.
Because I think you're gonna need something that's applies more constant on the course that, like I was saying at the beginning, like I think it's gonna struggle a little bit to push up this thing.
Mhm.
But I mean, I don't know. I don't know. When it comes to string lots, maybe it's fine, but yeah. So just I would think about machining these.
Okay.
Because 3D printing on 3D is gonna cost a lot.
Okay.
So, especially for the binding thing, it's just gonna make it a lot worse. I don't know if aluminum honestly is any better, but I just like.
Okay. Thank you.
I was just gonna ask you if you need perfect.
For the antenna, we have not. I mean, it's pretty. We could, but we're pretty confident that it's enough torque. But yeah, it would be good to have though.
The same.
Yeah, we can definitely do that, like testing it. Yeah. Cool. Yeah.
At all?
I mean, I have experience with cam because yeah, we currently don't have any cam developed, but yeah, it's just blocked. Yeah, I mean, yeah, yeah, we could. I can definitely do it. I can definitely like make a cam before C term, so we have it. Yeah. We would have to do trainings in C term. Yeah.
Is that you
The
like on the latch.
oh the dark blue.
The dark blue.
Well,
like I'm just thinking how what's the distance between the latch and where the force is being applied by the egg?
Yeah.
Like if you push it, is it possible that the force on that blue piece is just gonna like turn it instead of lift the entire thing up with the blue piece?
Turn it like I mean, it wouldn't be able to turn like from in this direction, but are you concerned of it like lifting one side up? Yeah.
Yeah, that was my thought. I mean, I guess if the like spring pieces are attached like fixed properly, then that should. I guess maybe it's just the perspective in here. I was thinking that like that's a really long like lever, but I think that's just the perspective.
Yeah.
And then for the forces that are going to be acting, so I know you did the forces on like the cross member, or like the latch mechanism. But my thought is those forces are also going to be imparting a torque on the like the spring pieces. Have you looked at all about like what that would look like?
We have not. We would have to analyze that further. Yeah.
I mean, I'm thinking it probably wouldn't be enough just like to matter, but if somehow that torque is high enough to deflect those pieces, then it might not be able to move up. I don't know if that makes sense.
Yeah, that does make sense, especially if it like deforms.
Yeah.
Yeah.
I mean, like if I assume they're going to be metal,
Yeah.
and that's probably not a concern.
Yeah, that's fair. We would definitely consider that, but I definitely want to test. We can definitely run some we can make analysis of that, stress analysis of that.
Yeah.
Before we
look at the forces on like all the components that
That's fair, yeah.
So I know you guys said you were reviewing first. I think that sounds like a great thing to be tested.
Yeah.
What question? There's someone who's probably. Okay, I thought that was not. Have you thought at all about like assembly on day of? Like how is the latch getting actuated? Because it'll need to be pushed up. And then rover goes in and it gets pushed back down.
Yes.
Can you actuate it from the other end?
You mean
Or can you like stick your
hand?
hand in? Yeah, like.
Yeah, that's the idea. Yeah. Ideally, there would be enough space. So when we push in the rover, we can just lift up that platform with our hand, and then like once we release the mechanism, once we land, we can then just actuate the servo. Our system can work.
Okay. Yeah, I was just thinking if you like need the servo to be actuated like by electronics.
Yeah.
And all of the actuating electronics on the rover, then you wouldn't be able to get the rover in to actuate the electronics.
That's fair. Yeah.
But if you like do it with your hand.
Yeah.
I think that's the great thing with this. The servo doesn't have to move.
Oh, that's right. Yeah.
It's
Oh,
stay
yeah.
at the horizontal position.
Yeah, no, that makes sense. Yeah, I think there's that. Yeah.
Oh, we are. Like Columbus.
Yeah. Thank you for the feedback. Oh wait, my bad. What was that?
I said I can do this.
Okay. Yeah.
His team's up here. His team's up here. Got it. Oh, that's no, we're good. Oh, I think I did this wrong. Yeah, sure.
You guys get ready for your picture.
Oh, we're doing. Okay, that one second.
I guess we'll have to wait for that.
Hang on.
Or the feet or legs up in the table, right? I don't know.
And if we talk, you guys here, so you're on the room. You're probably get a red line across your forehead. But you guys are not here. So you go a little bit. Yeah. And you guys are going to
Yeah. Definitely have that.
I think Haven, Nate, you.
Right.
Okay. Welcome to Rover Structures CDR. So I was going to first give a quick introduction to the rover mission as a whole. I assume everyone here is pretty familiar with this point, but we're going to deploy from the protective lander. Our goal is to be able to drive around on the sandy terrain using a screw propulsion mechanism. And then we will communicate through the antenna back to ground station, ideally sending live video feed or at the very least live approximate photos, as well as getting remote operated vehicle signals back to the rover. So that operators at the ground station could navigate the rover to an ideal recovery point. And if we ended up having enough range or we landed close, we could navigate all the way back to the landing site per Ezra allowing us to. So quick systems overview. That is not bolded. Okay. 3 tie rods will be running through the frame to enforce it. We now have batteries mounted inside the frame. We have an open MV cam on the front behind a protection plate, which we'll be using for obstacle detection. Drivetrain and motors are mounted in the back. And then the screws will be fitting inside of groove pieces in the lander to secure the craft. Finally, we've created recently a Mars board interface so that we can switch out as the Mars board gets iterated and updated without having to change the underlying frame. I think everyone's pretty familiar with the payload layout by now. This is from the top-down assembly where we're mounted in the bottom,
and the rover's forward direction will be facing down whenever on the craft. So our acceleration forces during the burn will be trying to push the rover forward. And we are clipped into lander from actuation's mechanism in the back.
Okay, so the first mechanical aspect is the load-bearing frame. So the frame will be printed vertically with polycarb, and then we are expecting a tensile force in the direction of the arrows with a maximum force of 312 newtons from the acceleration. And then we have the 3 1/4-20 threaded rods that have lock nuts and washers on them, and those will handle acceleration forces. And all of the forces will not be transferred to motors, electronics, or screws. They'll all go through the frame. And then we have an FEA analysis on the frame. The same, we have the compression force from the washer and nut combo, and the max expected compression force is 312 newtons. The force is applied by the aluminum plate that is acting on the front face of the rover. Even though the analysis shows a lot of buckling, this should be minimized by the tie rods. Our max deformation that our analysis showed was about 0.259 millimeters, and the max stress that we would ever experience is 2.47 times 10 to the 6 Newton meters squared. But that's really only in the spaces where we have the 90-degree angle right on the front of the frame, and we can minimize this with the tie rods, and then we can also fillet those corners as well. And again, the force is exaggerated because the rods can't be in the same.
All right, quick note about the Mars board mounting. So we want to have a removable mounting interface for the Mars board because the Mars board is likely to change. Specifically, the final flight version of the Mars board will have a different physical size, and we don't want to have to change the rover structure itself if and when the Mars board changes. So the Mars board slots in the bottom left image, into those slots there's grooves on the rover frame, and it slots into those grooves, and then the light gray plate holds it in from the side. And then in the top left image, you can see 2 mounting holes. Where those mounting holes are, there will be a gusset that attaches the Mars board to the frame to stop it from moving up and down, so it'll be secured in all axes. All right, now to talk about the drivetrain. All right, a few key drivetrain stats. This has changed a little bit. The gear ratio is 1-to-1, not including the built-in motor gearboxes. The belt is a 45-tooth, 3-millimeter pitch GT2 belt, and the pulley is a 16-tooth pulley of the same type. The screw outer diameter is 2.8 centimeters, but there is a chance that will change. And the used height statistic means specifically the height used by the drivetrain near the back of the rover. So neither the motor shaft or the hex shaft are cantilevered. We'll have they both are supported by this back plate here. We'll have bushings for all the places where the hex shaft goes through a plate to reduce friction, and the hex shaft will be cut to where the end of the shaft collars are in this picture. It's just the actual part goes longer, and we haven't reflected that in CAD, but they won't stick out like this. And then a few key critical components for the drivetrain. We have bushings, shaft collars, and the belt. And then right now we are planning to 3D print the GT2 pulleys, but we are looking into finding COTS versions of those if we can find them.
So for the screw design, we based our outer diameter and inner diameter off an IEEE paper. So theirs was 88 millimeters and 77.5. That's way too big for ours. So we kept the same ratio, about 1.135. And ours would be 2.853 to 2.523 centimeters. And there are hex shafts used to mount the screws into the chassis. Now for how the screws are mounted, use the L channel, and the screws are screwed into the L channel with grooves to match, and the tolerance is a bit higher so that the screws don't get any like damage before or when dropping. And to like get it out, they drive forward to screw out of the L channel. Now the front plates are kind of in two parts. There's one acrylic camera cover, and also covers the battery holders. And then there's an aluminum plate for that's load bearing, and that's like screwed underneath it. And they're screwed separately. The acrylic camera cover is screwed with these flatheads, and then the aluminum plate is screwed with these shafts. And then just another view of the aluminum plate, how it's machined from the front and the back. That's it.
Yeah, it's be a pretty simple, I believe, just a two-operation machining process, which we do in-house. And then real quick, so the battery mounting has changed significantly since our version of PDR. In order to save space, instead of having a normal to like the rocket's direction mounted set of 4 batteries, we're switching over to have 2 and 2 sets of these in series. We plan on using pre-soldered batteries with a JST connector per ESRA regulation, since you can't have vertical springs for risk of disconnecting. So I'll have these pre-soldered, and in these sets of 2, all 4 in series. These then fit inside of the main frame just above the screws and would be sealed in by the camera acrylic plate. So they could be easily accessed. You don't have to unscrew the metal aluminum plate to access them at all. Everything.
All right, so now we'll talk about the electrical side. Here we have motor requirements. So we set a self-imposed constraint of the ability to traverse a 10-degree incline with an estimated rover mass of 1.36 kilograms. Using a paper published by Lim et al. On the mobility screw analysis based locomotion and propulsion in various media, we determined that an individual motor torque of 1 Newton meter would be required to meet this constraint. So to satisfy this requirement, we selected the Dartbox V2HR. It's a 12-volt DC motor. It's made by Just Cause Robotics and has a stall torque of 2.686 Newton meters at 12 amps, and it has a mass of 60 grams. To control it, we went with the recommended WASP ESC. It's made by Robot Power. It has a current of 10 amps continuous and 30 amps peak, and it can handle voltages from 6.5 volts to 28 volts. It has a mass of 9 grams as well. Here we created a spreadsheet to assess the performance of our rover's theoretical performance. This presented here is the worst case scenario where we assume a 1 Newton meter torque for the entire duration of the trip. This gives us a current draw of 10 amps, approximately 10 amps, and a runtime of 17.5 minutes on a 3 amp hour battery. For reference, by the end of this journey, the rover will have climbed 127 feet, or approximately a 10-story building. So looking at a more realistic travel torque of 0.1 Newton meters, we get instead 2.37 amps of current being drawn, a runtime of 75.83 minutes, and a total range of 0.986 kilometers. So to summarize, here we have some key results. To reiterate, our max expected current draw will be around 10.24 amps. Our minimum time of operation is 17.58 minutes, and that gives us a range of 0.229 kilometers. Our expected performance will be a current draw of 2.37 amps, an expected time of operation of 7.83 minutes, an expected range of 0.986 kilometers.
There you go. Okay. What was the number for the feet it would climb?
127.
Yeah, you know those 127-foot hills in Midland, Texas. Uphill both ways. Okay, cool. So in terms of sensors that are going on board the rover, since PDR, we've simplified a bit. So we're still using the 2 current sensors, checking for if either of the motors are stalling out and could be in danger of sparking. We have these 2 DC current sensors. These should be able to handle whatever voltage and current the motors are running at. They both connect through I2C, so it shouldn't be too bad for wire ports. And then we switched over. Originally, we had some thermistors, which I believe that's what is still inside for the TMP36GC sensor. But this just includes integrated voltage bridge. So we don't have to build our own circuitry for that, which should make wiring easier. And again, these have a -40 to 125 degrees Celsius range. If you're curious what that is in Fahrenheit, there's the fun fact that -40 Celsius is exactly -40 Fahrenheit as well. So these should give us a Vout of 0.1 to 2 volts, depending on, and they scale about 10 millivolts per 8 degrees Celsius with a plus or minus 2 degrees Celsius accuracy. We're using entirely the OpenMV camera sensor for obstacle detection now. So we have scrapped ultrasonics and we're not replacing them with another similar type of presence or distance sensor due to just the concerns about how they would actually reflect off of bushes or whether they could actually see that well. So we're going to be using, most likely it's this didn't update, but the HR7 Plus, because the previous ones we've used are now discontinued. And for there, we will be running a similar script to the one run on Revelatio, the payload 2 years ago for bush blob detection. So we will be modifying that code to work in a horizontal plane instead of a vertical. So the image on I have no idea whether that is your left or right, but the fancier image, that's just a concept runner. It's not real code, but basically we run a similar blob detection for bushes from a rover about fixed height off of the ground. And then you can then do a trigonometric transform to calculate the distance and the size of the bush for each blob. And ideally, we'd actually be able to run going to a target GPS destination in the autonomous mode, which we'll get into in a second, where if we have our ideal trajectory, we could, in a very simple manner, not like true path planning, but figure out a PID control of how we could direct ourselves toward that trajectory while avoiding obstacles. Oh, the background didn't load. That's really sad. Okay. There was originally the full circuit diagram up here, but I think it didn't get transferred into the PowerPoint version. That's okay. It's all shown in like the separate images.
Hi guys. So I had an opening thing, but we're just going to zoom in right away. As you can see here, there are two sensors with a temp analog read in. That's the blue wire connected direct to the Mars board. There's one I2C bus with two current sensors and the camera, as well as two speed controllers and one servo connected direct to the Mars board using a PWM communication. As mentioned before, the batteries are 4 18650s stacked in series. So a lot of things will be getting power, specifically the 5-volt BEC converter, which will be getting power as well as the speed controllers direct from the battery. It's about going to be 16 volts, or more specifically 18.5. This is more of a close-up of our lander section. As you can see, there's a jack and pin situation going on. Things that are in this lander thing will be disconnected on deployment of the rover. In total, there are 4 servos, but all of them using PWM direct to the Mars. There's only 3 right here, as well as getting a 5-volt connection and ground from the 5 BEC converter. The brush motors get power from the speed controllers, which are in series with the current sensors, and the magnetic clip connector is visualized by these plug-in jack situations as a symbolization of how the rover will be detached from on deployment. So in summary, we'll have 6 PWM pins, 2 temperature analog read-in pins, 1 I2C bus with an SCL and SDA wire, as well as 3 sensors on the I2C bus, 2 current sensors, and an OpenMV camera. Now we move into software. As you can see, this is a mostly simple linear state machine. So the first thing happens is initialization. If the IMU detects that we have landed, it will complete a self-writing protocol. If that is completed, then the actuation clip will releasing our rover. If the clip is released, an automated drive out for a fixed distance will initiate. If it's driven for a certain time, the antenna will deploy. If it is unable to deploy, it will go back to the automated drive out for a fixed distance. If the antenna does deploy, it will be waiting for a connection, which will either, if we get connection, our ROV state will ensue, which will be manual operated or an autonomous mode if about 10 minutes of without connection has elapsed. Then we move on to the state machine for the autonomous mode. We have a continuous state checker interrupt, which is constantly checking if a connection has been lost. If connection has been lost for more than a few seconds, we will immediately move into the autonomous mode. And this will be a sensor input is taken from all of our sensors. It's gone into sensor processing and then gone into the encoding mode, which will kind of compress all of our sensor data together and set it to the antenna. The antenna will send this information to the ground station, as well as ground station information being sent to the antenna. This will go into command processing block, which then turns PWM signals into the speed controllers and the motors, translating kind of high level data to low level to control the motors through autonomous mode. The state machine for the autonomous mode, again, the constant state checker interrupt to see if connection has regained. If connection has regained for more than a few seconds, we will move back into the ROV state. So constantly checking for connection. If unable to connect to ground station, autonomous state driving obtains. This is for our obstacle intervention. So if there is an obstacle and it's unavoidable, we'll idle. And if it is avoidable, there will go into this obstacle avoidance data, which was talked about before with Alex, where it will be able to rotate based on the distance and the trigonometric calculations. If it is unable to avoid the obstacle, it will idle, reverse, and rotate until the object is able to be avoided. If there is no object, then it just keeps moving forward. These are our citations, and is there any questions?
Yeah, Nick.
I think you also got this, but you have a lot of those state transitions dependent on knowing the states of certain mechanisms. And as of right now, most of the mechanisms that moment. So like you talk about if the latch were able to be successfully pushed up or if the antenna would be successfully deployed, and currently your like servos don't happen. Any way of knowing whether they've done that, and you don't have a sensor on the payload that have the ability to tell you way of knowing if those things have happened. So you plan on guessing.
Yeah, no, that's a good point. I mean, this is phrased as like these if statements. In reality, I think it will mostly be just dead reckoning for a lot of the servo runs for a point. I don't believe Lander is putting in like limit switches or positional feedback for. If Lander ends up doing that, we will certainly incorporate a checker for like once it's complete. Yeah, for like the self-reading. Yeah.
That is my question.
Mm-hmm. Yeah.
PWM service we can get with
I remember those had a lot of issues last year for like Lander.
just like simple ones. But that's not
Okay.
to you.
Yeah. So as I said, like if any of the other systems, because those are all sort of outside of our actual like electrical systems that we're designing, if those systems end up incorporating like feedback that we can get back from that, we'll include an actual checker. Otherwise, I think it'll just be dead reckoning. Are there questions from the sheet?
We have questions.
Oh, okay.
Well, I have a couple just quickly. If you like to slide 18.
Gotcha.
I know that's a lot of slides.
Is it like, sorry.
There's actually a line now. Yeah.
Okay, yeah.
So do you have space to mount the radio board that we're gonna need and then also the GPS antenna?
I believe we do. There should have, I'm looking at if I get one slide over actually, if you look at the current top assembly, there is space. I know that isn't fully used yet. So I would like to see the dimensions. And
Okay, we have those, we've had.
Okay. Cool.
So
we'll incorporate those into the CAD. Yeah, I'm sure we can.
okay, and then. Sorry, you guys asked.
Okay. Yeah, I have a question. So, do you think the batteries can supply 10 amps at that one unit you're driving?
That is a good question. I believe we looked at the ones we're using. Yeah, it isn't. The only slide that's talking about, sorry, I don't have the actual data sheet on here. It is in the BOM if you want to take a look, but the ones that we're using, the one that's pictured here, that is a 2000 milliamp hour. It's not as high quality. We're just using it for prototyping because it's pre-soldered.
Yeah.
I think the nicer ones that we could get and then we'd solder ourselves. That is that in series. I think we'd be able to discharge 10 amps. Is that?
Should look at the C ratings.
Yeah.
Okay.
Yeah, because then if you drive too much current, the battery will drop.
Yeah.
Like burn out and do resets and stuff. But luckily, we already planned to do the current sensing for the rotors.
Yeah.
So I think that you just need to pay attention to that and figure out what you have to limit it to in software.
Yeah.
Don't spin the motors this fast.
I'll double check on the battery rating. I believe it was higher when we looked at it a while ago, but I don't have it off the top of my head. It's all the numbers from like those later slides that are like talking about running like 10 amps of constant current. Yeah. I think they're there and they're valuable as like a low bound expectation, but we should never actually be having to output that much current. So yeah, no, we'll in software, in autonomous mode, always be having a checker and warnings in the ROV mode. Yeah.
So this one look pretty good. So is that what this whole structure is 3D printed?
Yes.
So what did you guys assume, like what material did you put into the FDA adoptions for this?
We put in SolidWorks as a ABS PC. So we're assuming to print it out of polycarbonate.
And what do you know that is?
I actually don't know.
Because I think most of the time they assume 100%.
I think with the SolidWorks, it's not assuming 3D printed actually, so that is a higher, like is better.
Well, so what I'm saying, what I was gonna say is we don't have to print 100%. That's just the way it's built. So your force, basically everything that's outputting with this is going to be higher natural because we're gonna have some sort of fill inside. So just keep that in mind when you have to run it. Yeah, like it's kind of hard to run FDM because like layer heating can really change how much it actually thinks.
Yeah, I remember for the previous one, just on like using a like PETG, I think at the time for some of everyone was concerned at the time. There's a paper I found that like analyzed the material as the infill drops. I don't have that for polycarb right now, but I'm sure I can find a similar type if we wanted to like create a custom material to look at it at a certain infill.
It's just hard in general.
Yeah.
Just like take the FDA do let's just say what they're going to solve.
Yeah.
Be great. Like I'd be more inclined to just look at the rods and see if they can support it. And like if the 3D print's there to help them, that's great. But if the rods were into it and it was support themselves, that would be a better.
Right. Yeah. So I mean, this is both grain of salt in a negative way because it's 3D printed compared to like a cast or other composite material. But I would say this is a worst case scenario because this is looking at mostly buckling deflection is what this is showing, not true compressive. Whereas, yeah, we can run a buckling simulation on the threaded rods, but at 1/4 inch, 3 of them, my guess is that the rods will reinforce and stop nearly all of that buckling. Yeah, we'll get that.
What is this if you did like CNC kitchen and testing actual PC life? It's good running at 100% infill.
Really? It's 20% infill for that thing? Oh yeah. That's gonna be more.
I don't expect we'll need 100% fill. I think I'll check to see if I can find how the elastic modules will drop.
Oh.
Yeah.
And on the note of this, I'm just curious, like, if there is a lot of deformation with that, like, harm the actuation system, like the ability of the rover to like of the latch to, because
I mean, so this is
It's not how it's.
no, I know.
Yeah.
I'm just saying, it would like, is there a way where we can do the simulation with rods?
yes, there is. I think
Because that would be nice, just for peace of mind. That
this was we added this quite fast, so it was done rushed. Yeah. No, we could definitely look at it with your rods. I think it's a little more complicated to do, but I don't think it would be in danger of harming the antenna that much. Like, I mean, this is 0.2 millimeters, so even grain of salt, less than a millimeter of deformation. Oh, the latch. How would that endanger the
Well, if
latch?
there's deformation on the side where actuation stuff is going, that deformation.
But if it's gonna deform, it's gonna deform. That needs to, that's true, it's gonna be closer to.
I mean, the force will all be on the latch,
Maybe
but
like, that's the unfixed part, because that much.
yeah.
So it would deflect farther up, not here. If it deflects to the base, the rover is cooked in.
Yeah, and we'll also we can add more. This is the shape of it is for giving exposure for just to ease of use for electronics. We can add lots of more supports to prevent buckling at that back part.
We have more questions if you guys want to. Is there someone after us? Yeah. Sometime. Do you guys have to go?
I don't think so.
We're good. And I have time to say this is what comes.
Thank you. Whenever we do finish, I have a box of donut holes for anyone who wants them, though. So incentive to at some point.
160.
Oh, the slide.
Yes.
Oh, HL 160. Yeah. Focus on Monday.
Sorry, what?
Slide 93.
Okay, 91. Gotcha.
Are you sure that you can scale ratios like that? Was that in the paper?
Yeah. Okay. That's good question. Yeah. So the paper was using 88 millimeter outer diameter to 77.5 millimeter inner diameter. So yeah, there was two thoughts, and they found that was the ideal ratio and dimensions. We obviously can't fit 8 centimeter tubes because that's the entire payload then basically. So yeah, we're starting with the reason we made like going full for the ratio was mostly that in order to just find bearings, especially flange bearings that can actually fit and wouldn't be dragging, by making the inner diameter a little bit larger, we guarantee that the flange bearing, like the my cursor does not show up. Okay, but the bushings up there, those flanges aren't going to risk dragging on the ground in any way, because with the absolute they were. But we can. The nice thing about this is it's pretty modular. We can swap out screws day of in a couple minutes. So we're gonna test a few different like versions.
Yeah, because I was saying, my guess would be that we should have cut smaller and smaller as you get to a smaller scale, just because. That would I guess. I just don't know. I don't know if the ratio is going to be exactly like transferable.
I think yeah, the more you keep it closer to the absolute like ratio or the absolute difference, the better traction you're going to get, and the more you keep it closer to the ratio, the less friction and like the better efficiency you're going to get. So finding the optimal one will sort of be a balance of like we don't want to induce slipping, we want to be able to have good traction, but we also want to have good power efficiency and be able to fit well on the sand. Yeah.
What are your questions? Everyone has questions. You guys keep asking questions.
I had a note. I think we don't trust TPU in the desert, especially in the belts.
We're not using TPU. What?
For the timing police?
Yeah.
The belts are
Oh.
caught.
Yeah.
Yeah.
Okay, good.
No, we're not. We already have them. We're not using.
There's something that's TPU, is it?
No, there's everything.
The old prototype for the rover.
Oh,
used TPU belts. But that was like last year, I think.
I mean, the one I made on your team last year used TPU, but that's not.
I thought you said it.
No, it's polycarb for all the load, like the high load bearing parts, and then probably PET G for anything that's under less stress. We might for other things that maybe need more heat to do nylon or other materials. But any other questions? Also from the audience, anyone else? Doesn't have to be.
Some questions, slide
85.
Just with the Mars work.
Yeah.
I understand what you're saying with the dimensions changing.
Yeah.
And we didn't have those, like at the beginning of the year. I'm thinking like so the dimensions were finalized like a couple of weeks ago. I think it might be easier to just be able to mount the board directly to the rover.
I think for the real one, we probably will.
Yeah. So instead of having to worry about like the secondary, there's just a lot of things that I was thinking, like all the connections, like that come from the board, like we'll need the SD card, like USB connections, that might be difficult to do when with the clocks there.
Yeah, I think the interface would be for the prototype mostly, because there's the ones that are currently out. I know it's finalized, but I don't think it's produced yet, right?
We don't know. We don't have the.
Yeah, and since we want to start software testing essentially now, because there's a lot of software to code. I think the interface is just so that like we can be using the current one, and then in like a couple hours we could print out a new interface box and switch over to the new one. But then I think the real one, yeah, we just have it directly screwed on.
Yeah, because no, I mean I know what you're saying. Although we should have boards by like beginning middle of C term. So hopefully that won't be an issue for too long. You have
The only reason we would include an interface box in the real one, like the convenience of being able to pull out the board is maybe a little bit nice, but as long as we're able to wire it just by moving the rover, like, I don't think it should be needed.
Like doing all those connections with the box around it.
Yeah. Yeah, we can also cut any holes in this box as well. Like it can be, it really just has to have the bottom of it, not the
And then,
top.
yeah, so then how is the box fit into the rover itself?
Can you repeat that?
How is the box mounted to the rover itself?
I'm not sure how well you can see because it's dark gray / black. But right here, there are slots in the rubber frame, and there are what's the opposite of a slot?
Rail, I guess.
Oh yeah, a rail.
Yeah.
On the bottom of the box that slides in there, and then it gets held in by this plate here, sideways, and then on the other side next to the motors, there's going to be a little gusset that will hold it in so it doesn't fly up.
I'm so sorry. That is truly invisible. Like I'm realizing now, it does not. Yeah, it shows up on a screen, but
there are slots there.
Wait, so what is the white piece?
The white piece is connected to the frame of the rover with screws.
It's just a cap, basically.
Yeah.
Slot in and then cover the slot.
And if we wanted to, we could actually probably make that part of the Mars board box.
Take a word too.
How does the board?
No, you're
There's
good.
a secondary screw at the moment. We might have to make a T-shape for LPI.
Channels are just planar, right?
At the moment they are. Yeah.
The channels don't do that. These at the right. Can you see the cursor? No, you can't. Okay. Top left picture. It's also hard to see. I'm sorry, moving colors, but there's a hole in the box and there's a hole on the frame, and there'll be a gusset between them.
Oh, gotcha.
And that screws in. Yeah.
Oh, I see. I didn't see it.
Sorry, the colors do make it hard to see.
Yeah. I wonder if it's easier, if you could do like a dovetail for your slots, and then you just.
That's
Yeah, we could do that.
Would it not be easier to just do it right here?
Like, they're on application.
Yeah, but then you.
It's not the material of the belt.
Oh, yeah, that's each side. Like, is there anything?
No, there's not.
Like, couldn't you just mirror that white part and screw it up?
It could still go up. box then, unless you're thinking of something else.
At the moment it can, but
Yeah.
One more thing to mention, you might have this already.
Yeah.
There will need to be some amount of clearance between the bottom of the flight computer and that box there.
Yes.
That'll need to be on like slight.
We don't have that yet, but we can put that in.
I don't think we have standouts like printed in, but we put heat sets and then you can put standouts on top. So. And I think that is actually pretty okay on height. It's not too close with actuations system. Like if that moves up like a millimeter or something, we're not, sticking out.
So we will also, depending on the orientation of the SMAs, like.
Yes.
If you have a 90-degree SMA vector.
Yes, yeah.
Up and then sideways. But if for some reason we can't use that, then there'll have to be like space with the wire to do the.
Yeah, I know the only issue is just the plate going on top of it. So if that plate, which I think can move up a tiny bit and it won't cause issues. The only part that's tight right now is the OpenMV cam. We're gonna try and optimize that a little bit to move it lower down because it's almost touching our cross member right now. But other than that, yeah, the height we're not too cracked on, I think.